Yeah, thank you for the introduction and thank you for the opportunity to present at this workshop. I'm going to present dispersion of salmon lice, connection between farms and economic costs. And I'm going to present this in the context of what we're currently working on fish scaling and actually how all these parts are connected in our work. So to start with, fish scaling, Faroes farm of Aquaculture research station. Our main goal, aim with regards to salmon lice research is to develop knowledge for a tool which can be used for optimal salmon lice management. And in order to achieve this, we need knowledge of lice dispersion, connectivity, salmon lice population dynamics, and also lice economics. So down here you see another farm that Esbjørn showed, one of his farm. This is another example from Faroes where we used our model to predict the lice development on a specific Faroes farm. So on the y-axis you have lice per salmon, and x-axis you have time. And Faroes farms are mandated to count lice, or lice stages, or salmon lice stages, bi-weekly. These are the red dots or circles here. And our model is the black line here. And when the farms reported doing treatment are these vertical gray lines here. And we see that there's great agreement between the model and the lice counts. And this, of course, this means that, in principle, this farm could have come to us in the start saying, okay, we want to put this amount of fish out in this period, and we could, in principle, have predicted the lice development throughout the production cycle, given that we know the efficiency of the treatment and so forth. So this, of course, in itself is useful, and we can use this kind of model to identify optimal lice or treatment strategies. Can you see? So before we get started with dispersion and lice population, we need a bit of background knowledge, biological background knowledge. So here you see the salmon lice life cycle, which consists of 8 stages, where the first 3 stages are planktonic, so they produce larvae, they go into the water. And the first 3 are planktonic, and then they find a farm and they go through 5 stages on the farm. These first 2 stages here are non-infectious and take about 4 days at 10 degrees water. And the second stage is cocopodiate, which is infectious and can survive in water for around 13 days. So they have around 70 days at 10 degrees water to find a new host in the environment. When they attach the host, they molt to calamus 1 and go through these 5 stages and become adult female or male. And this takes, from they attach to they can produce a female again, takes around 47 days at 10 degrees water. And we know a lot about these stages or the development time due to very good work by Hamre et al., which I know Susie here is highly involved in. So to look at dispersion of the planktonic stages, we can use a dispersion model, which is a particle tracker model forced by a hydrodynamic model. So ideally you would use a fully forced 3D model, as they do in Norway using ROMs, or FRECOM as they do in Canada or Scotland. But we in Faroes, however, don't yet have a fully forced model with sufficient resolution yet, but we're working on this part. So for this dispersion work, we used a simplified barotrophic model, which is essentially 2D, where we used 6 tidal constituents, the residual current, and we had a very good resolution of 100 meters. The The reason we can't do this in Faroes is because the currents around Faroes are mainly tidally driven. So that's why we can get away with such a simple model. The particle tracking model is Lagrangian mechanics, uses Lagrangian mechanics, so it's just following the particles depending on the currents. And the biological parameters are also fairly simple. We just follow the length of the planktonic phases, so the phase 1, the Napoli stages, around 4 days, and 30 days in the coprolite phase. And we use a mortality that's normally used in these kinds of models of 17% per day. There are more sophisticated particle tracking models used. For example, if you know the Norwegian traffic light system, they use a particle tracking model where the lice, or particles that resemble lice, are sensitive to both salinity and light. So here, me and Espen didn't synchronize our presentation, so I think you can see this movie again. So here we release 16 particles every hour for 2 days from all the defined farm sites in Faroes, and follow them for 2 weeks. So we see, as before, that fairly fast after they are released, they start dispersing around Faroes. But we see some places particles are more or less stationary, and that's because the model doesn't resolve the currents inside the fjords, either because or mostly because there aren't any tidal currents deep inside the fjords, so naturally the particles can't escape these fjords. But if they do escape, they will disperse far and wide, and they sort of form a tidal dispersion highway which goes clockwise around the Faroe Islands. And we also see that the southernmost islands looks more isolated from the rest of the Faroe Islands, as very few of red particles released here go up to the rest of the Faroe Islands. So we also found that, or we did some calculation on the distance traveled by these particles. So particles could disperse up to 120 kilometers from their release site. Over 50% of particles in Faroe Islands traveled more than 40 kilometers, which is a lot. To give you a point of reference, in Hardangerfjorden we found similar results where particles can, Hardangerfjorden in Norway, where they can disperse up to 100 kilometers, but in for example Scotland, in Loch Lynn, they only traveled at a maximum of 30 kilometers, so it's very determined on local conditions how these particles disperse, of course. You can use these dispersion models to investigate the connectivity between farms. So apparently the grey color doesn't show this map, but this is a map of the Faroe Islands. It's fine with the computer. Well, never mind. So we looked at how many particles go from one farm site to another or their own, and you can do these connectivity matrices. So we defined 24 farm sites where the white areas here are the emitting sites, so that's where we release particles, and the receiving sites are these blue area around the emitting site. So if a particle enters the blue area, we count it as a connection. And in the simulation, we released 900 particles every hour for 83 days. And particles were allowed to live out their planktonic lifespan in the simulation. And we only recorded a particle connection once in any given farm. And only coprolites, so particles older than 3.7 days, were allowed to infect a new farm. So here we see the results. We see these three connectivity matrices here. So we have receiving farms, so the 24 farm sites here on the receiving on the y-axis and emitting on the x-axis. And above here you see just the percentage of particles going from one farm site to another. In the middle here you see the mean age of the particles in these, or lice in these connections. And down here we have included mortality, so this was maybe the most useful matrix here. And there is of course a lot of information in these kinds of matrices, but in essence we can say that it forms a complex and highly connected farm network, or the Faroes farms form a complex and highly connected farm network. And they form at least two, so here is one cluster, and it looks like for now the rest of the Faroes farms is one cluster, so there's at least two clusters of farms in Faroes. Yeah, so now we move to salmon lice management. As Espen also talked a lot about, salmon lice are usually managed with treatments, and a rough estimate of the cost of lice in aquaculture is somewhere between 0.25 to 0.39 euros per kilo harvest salmon, which translates to somewhere between 675 to 1 billion euros if we have a global production of 2.7 million tons. When treatments are required, it's mainly regulated with lice treatment thresholds. This varies from country to country. For example, Norway has 0.5 adult or gravid adult female per salmon, but 0.2 in migration periods. In Scotland, it's recommended to have 0.5 adult female per salmon, but the regulation, or if it's more than 8 adult female per salmon, that mandates intervention. So, and in Faroe Islands, we recently lowered our treatment threshold down to 1 adult female per salmon, where we have 0.5 migration periods. So there's a lot of difference, and a question you can ask in this regard is, what is the optimal treatment threshold? And we looked at this in a paper of ours in 2019. And to answer this question, we developed a conceptual bioeconomic model, which is an economic model coupled with a combined salmon growth and salmon lice model. The economic part is, although this equation looks maybe a bit complicated, it's fairly simple. You just calculate profit per time. And this term here just calculates the profit of the harvest, and this term here calculates the cost of treatments throughout the production cycle. And we use the salmon growth model to calculate the salmon weight, salmon survival, and also the time of harvest. And in the salmon lice model, we used to find out the number of treatments, when they do the treatments, and also here we set in the treatment threshold. So here's my attempt to explain the salmon lice model. This can be explained in many ways, but we can represent the salmon lice life cycle with this box model here, where we put the first 5 attached stages in these 3 boxes here, and we made an additional box for the gravid females because we want to know how many produce larvae. And a model is in principle very simple. So all the lice that come to a farm site come from either external resources or internally produced. So if we put more farms together, so this is a homemade picture of an island, and we imagine that this is a farm system with 3 different farms. So here we make a model for each farm, and we can use then our knowledge from the dispersion that, okay, they produce larvae here, which travel to, we call this farm 1, and go from farm 2. Is it the one? Yeah, oh yeah, they go from farm 2 also to farm 1. So we can use the dispersion model to also estimate how many lice come from the other farms and use that information in population dynamic settings. In this work here, we also added 2 additional parameters. So one was the cost of lice on salmon growth. So we said in the model that, okay, if there's very low or 0 lice, salmon grow at 100% capacity. But as you get more and more lice, the salmon will grow slower. So here they don't grow at all. 40 gravid lice per salmon, which is a lot, but not unrealistically high. So there is a cost of having lice in our model. And also we added a Lie effect, which says that if you have very low abundances of lice, the chances of a male and a female fighting each other in a net pen is lower, and therefore females aren't fertilized all the time, and therefore the percentage of or number of or the larva production will go down. This I can maybe add that this parameter hasn't been proven finally, but this is, some people believe this is present, but it's very hard to show from real data. So we go to some of the results here. So here we looked at a 5x5 or a 5-farm network system. So here we have treatments per farm per cycle, production cycle, and here we have profit as euro per salmon per year. And we looked at 5 different connectivity settings. So we have an isolated farm which doesn't have a connection to any other farm. And we looked at directional cyclic, so you can see that as a fjord system where current goes out in this one direction or this direction. And these 3 systems here are symmetric. This is equal, so this is just equal amount of connectivity between all farms. Diffusive is just connectivity decreases with distance from the farm. And directional cyclic, which can be seen as an island where the current goes out around in one direction. So if we look at the profit, we see that isolated farms have fewest treatments and therefore highest profit, whereas these systems are very like in their results and have lower profits than the other systems. So we've tried to sum this up more clearly. So here again you have profit per salmon per year, and treatment threshold here on a logarithmic scale on the x-axis. So here you have a system where we had looked at 0% connectivity, so an isolated farm, 0.1, 2.5 and 5% connectivity between the 5 farms. We see that if you're isolated, you profit the most by waiting as long as possible before treating your fish with lice. So here it's almost 10, somewhere between 5 and 10 gravid lice per salmon. But if you're in a connected farm system, you profit most by applying a low treatment threshold, which is here down to around 0.1 gravid lice per salmon. And if you look at, now we take all the connectivity away. Now we keep a constant 2.5% connectivity, but we look at turning up and down the external background infection. So that's the wild salmon that always are present in the system. And if that is very low, you will have an optimal peak that will be at the lower treatment threshold limit, and you will have in principle higher profits if you have extremely low external infection pressure from the background, and this goes up as this parameter increases. We also looked at, or we showed that there is a case of tragedy of the commons in farm or farm networks, salmon farm networks, when we regulate with a low treatment threshold. So we did an experiment where we said again a 5-farm network where there's equal connectivity of 2.5%, and we said okay, every farm has to treat at 0.1 gravid lice per salmon. But when we looked at, okay, if one farm cheats and say, okay, I will circumvent legislation and use my own, and use a 10 gravid lice per salmon treatment threshold, then you see that if one farm cheats, or 0.2 proportion, his own profit will increase considerably, while the profit of the whole system will decrease. But this, and as more and more farms cheat, this sort of benefit of cheating goes down. But what is not so straightforward is that the system is least profitable when around half of the farms are cheating. So this actually indicates that if you manage a system with a very low treatment threshold, you need very strict regulations, so everybody keeps to that treatment threshold. Then if you can't do that, it's maybe better to use a higher when you think of the profit of the whole system. So if you just run through the conclusion, so in the dispersion connectivity, we saw that there was a dispersion highway that goes clockwise around the Faroe Islands, but the Faroes, or the southernmost island, was relatively isolated. And the Faroes farms form a complex and highly connected farm network, and we have at least 2 farms, or 2 clusters of farms in Faroe Islands. And in the lice management, we see that we have 2 optimal treatment thresholds peak. If you're isolated, you profit most with waiting as much or use a higher treatment threshold, except if you have really high self-infection or really low treatment efficiency. Connected farm networks with overlapping production profit most with using a relatively low treatment threshold, except if external infection pressure is really high. It doesn't matter what you do. It just goes up past this Ali effect that I showed you before. And tidal commons is present in connected farm networks with overlapping production, and farm network profit is lowest when around half of the farms are cheating, and yeah, which I mentioned just before. So in future perspective, so as mentioned, what we're trying to do at Fiskalning is apply this knowledge. So what I showed you before was a fictive or idealized system, but now we're trying to sort of take all this knowledge and put it into a real and model a real system. And we've been lucky to capture some of the dynamics from real farms in Faroe Islands. So we're trying to couple all these aspects together, and our goal is to maybe make a tool which can be used to plan that Esbjørn showed. So it's in very early beta stages, but so it's already being used to some extent. So this is something that we also look forward to working with. But it requires much more work or additional work in hydrodynamic models, connectivity. We can still increase our biological knowledge of salmon lice a lot, and we also need to know more about population dynamics, treatment efficiency, cleaner fish. There are a lot of things we can still work on. So there's still a lot to do in this field. Thank you. That was it.
Any questions?
Good.
Thank you. Very much. I have a little question. Very interesting with the models here, but I have one question because you mentioned, for example, in Norway they have legislation saying 0.5, 0.2 female lice per fish, and you mentioned that you have about 1. I mean, if it's only 1, it has no impact on the fish growth, right? It's just a little lice crawling there. So I mean, in the real life, you must have some, at least some seasons, some higher levels. So what do you actually reach? Which intensity of infection do you reach when you examine your fish? Maybe you know that as well.
If you go above the treatment threshold, then you get, how you say, clips. And if you have too many clips, you have to decrease the production in the next cycle. But that has not happened yet. That you have to decrease the production? Okay.
Great, thank you.